On the board and triumvirate of authors. The oath will be given by Eugen.
Thank you very much. I would like to thank the organizers for inviting me to participate in this program. So I'm going to speak about some joint results with Adrian, Constantin, and Walter Strauss. So this will be about two-dimensional steady gravity waves with constant vorticity, existence of solutions of large amplitude. So although I will be speaking about traveling waves, so let me start with a quick derivation of the relevant equations. So we consider water in 2 dimensions. So water is inviscid incompressible fluid. So the dynamics is described by the Euler equation. We consider as the only force, external force, to be gravity. So the fluid domain is bounded below by a rigid, by a flat horizontal bottom that we locate on the real axis, and it has a free surface, which, for simplicity in this introduction, it is assumed to be the graph of a function of t and x. And so we have the usual Euler equations with incompressibility and the usual kinematic and dynamic boundary conditions. So we will be interested only in traveling waves. So we assume in what follows that the functions have x and t dependence only on the form x minus ct. So both the fluid velocity and the pressure. And we work in the moving frame. So we replace x minus ct by x. And so we are led to a stationary problem in 2 dimensions. Because of the incompressibility, it is possible to introduce a stream function in the usual way, and eliminating the pressure from the equation leads to the fact that the vorticity of the flow and the stream function have parallel gradients, and so the vorticity is a function of the stream function. Let's say, in fact, this gamma can be arbitrary function, but I will consider for the rest of my talk actually only the case when gamma is a constant. So note that my definition of vorticity is different in sign from that which is sometimes considered. But so this will not make any difference for the remaining part of the talk. And so all of the equations and the boundary conditions can be, for this kind of steady waves, can be expressed in terms of the stream function psi. So as I said, I consider constant vorticity, so delta psi equal gamma. Psi is constant on both the bottom and on the free surface, and we choose the value 0 on the bottom, and then we also have this condition called the Bernoulli condition, which comes from Bernoulli's theorem and the fact that the pressure has to be constant at the free surface. So so this is a free boundary problem. The surface of the wave has to be found as part of the solution, and throughout what follows, I am going to consider spatially periodic solutions, and you can see here 3 periods of the wave in the picture. And I am not going to make, for a large part of the talk, I'm not going to make any assumption about the geometric shape of the free surface. So it could be an arbitrary curve. So because we have all these constants floating around, so I'm going to write the equation on the board so that we have them for reference later on. So delta psi equals gamma, a constant, psi equals 0 on the surface, psi equals some other constant that we call minus m, so where m will be the flux, And then on the free surface, we also have the Bernoulli constant pressure condition, gradient psi plus 2gy equals q. So the axes are chosen so that the bottom of the fluid domain is the real axis, and the coordinates are capital X and capital Y. So again, g is the gravitational constant, is a given constant. Gamma is given, and the flux m and the Bernoulli constant will be parameters that will vary along the solution set that we are going to discuss. And the period of the wave is will be a positive number L that we write in the form 2 pi over k, where k will be the wave number. And then so the coordinates of the troughs, so let's say of the lowest point, we choose them to be at pi over k and minus pi over k. So this is the description of the problem that I will consider throughout what follows. So since this is a free boundary problem, existence theory usually follows after transforming it into an equivalent problem over a fixed domain. And okay, but before saying that, I was going to say here. So let me mention the type of questions that motivated our study. So we are interested in whether there exist waves for which the free surface is not a graph but is an overhanging curve, like in this picture, and also in waves for which even though the free surface itself is a graph, the streamlines, the level set of psi, are not all graphs of functions, but there are some regions bounded by streamlines, so these so-called critical layers. So, and prior to our work, there has been a little rigorous analytical work on this kind of issues. So, in the case of zero vorticity, irrotational waves, it is known that any solution of the water wave problem necessarily has the free surface as the graph of a function. So, such things do not exist when gamma equals 0. Such things also do not exist when gamma is 0. On the other hand, for constant non-zero vorticity, there has been numerical work that calculated that suggests that such waves do exist. So this problem has a long history. So the first suggestion that there exist waves with a constant vorticity with critical layer like this can actually be found in the paper by Kelvin in 1880. So the speed of propagation for linear waves in terms of wavelength seems to me that it appears in these papers in the 50s. And a further, the first rigorous existence proof of waves with constant vorticity and critical layer, so waves like this, is due to Eric Valen in 2009. Okay, so as I said earlier, for existence theory, it is usually necessary to reformulate the problem in an equivalent way over a fixed domain. And this is a brief summary of the methods that have been used. So they can be classified into two categories. So some which are specific to irrotational waves, and some which are valid for a general vorticity function. So those for irrotational waves are usually based on complex analysis and singular integral equations on the boundary. So we have the equations of Nekrasov, Levi-Civita, Babenko, and also we can use the Dirichlet-Neumann operators. But this is just for irrotational waves, while for waves with general vorticity, so there is the transformation of Dubreuil-Jacotin, and there is also that has been used by Constantin and Strauss and their 2004 paper, proving existence of waves of large amplitude with general vorticity. Okay, and there is also a flattening transformation, but so neither of these two is able to handle waves with overhanging profiles, which was our aim. So while the first three methods are restricted to irrotational waves. So the method that we use to study waves with constant vorticity, so is actually an extension of Babenko's formulation, so which was originally for irrotational waves of infinite depth. So I'm going to show how the problem of waves with constant vorticity and of finite depth can be equivalently reformulated as a pseudo-differential equations involving some Hilbert transform, so an extension of Babenko formulation. And using this formulation, so we are able to prove global bifurcation theory, so constructing waves of a large amplitude, which in principle could be overhanging, although we have no result proving that overhanging waves actually exist. So the aim of my talk will be to explain to you how this generalized Babenko formulation is derived and the global bifurcation theory that we have given. So okay, so this is the equation that we obtain. Now it is a bit unfortunate that the notation is a bit unfortunate in that now I am using v for a function of one variable which does not have anything to do with the velocity field. So we should forget about the velocity field. So throughout what follows, v will be two pi periodic functions of one variable, whose connection with the water wave problem is that for any solution of the water wave problem, so this is a parameterization of the free surface in conformal coordinates. So v is basically the vertical coordinate of the free surface of the wave in the conformal parameterization. So vertical coordinate is v. This ckh will be Hilbert transform for a strip, so which depends on the product k times h, where k is the wave number and h is some new parameter that arises in the problem. So this so-called, what we're going to call conformal mean depth. Okay, so so this is the meaning of v. This is the connection with the free surface. And for a solution of the water wave problem, so this is the equation to be satisfied by v. In black, we have the terms which do not depend on the vorticity. In blue, we have the additional terms that are due to the presence of the vorticity. So in the case of infinite depth, so this ckh is replaced by the usual Hilbert transform, and we get the usual Babenko equation. So is the first line written here. So while the second equation that we have, so is something okay, a bit surprising at first sight, but so square brackets will be used to denote averages. So this is just saying that the average of this function here is equal to the average of this function here. So the second equation is an equality between two numbers, while the first equation is an equality of functions. Okay, so we have, as I said, all the constants in the problem occur in here, and in addition there is there appears another parameter h, such that the average of v is h, and the h will be the conformal mean depth of the fluid domain. So yeah, so I intend to show you how this equation is derived. So this equation just in one variable. Ckh is a linear operator, and then show how we get the existence of large amplitude solutions using global bifurcation theory for analytic operators. So in the case gamma equals 0 and infinite depth, so such equations has been extensively studied by Buffoni, Dancer, Toland, and collaborators. Okay, so first let us start with the simplest solutions of the problem of our problem. So these are waves for which the free surface is horizontal and the flow is a parallel shear flow. Now we can write down these solutions explicitly. So seeking psi as a function of y only, and we have this formula, and this is the velocity field. So in a flow of constant vorticity, the idea is that the horizontal component of the velocity depends on the vertical coordinate linearly with slope gamma. So so graphically, this is how such flows look like. Yeah, so this is fluid velocity depending linearly with height. And such flows can be either unidirectional, so all particles move in the same direction, either on the left or on the right, or bidirectional, so in which some particles move on the left, some on the right, and there is a line at which psi y is 0 where the particles are stagnating. So this is a one-parameter family of trivial solutions from which the non-trivial solutions will be proved to bifurcate. Now, perturbation analysis, but rigorous in the setting of bifurcation theory, tells us how the streamlines look for small amplitude waves, which are perturbations of such flows. Namely, if we perturb a flow like this, very, very slightly, then for the resulting stream functions, the streamlines will have a very simple structure. Would be graphs, all would be graphs of a function and almost flat. But on the other hand, so if a bifurcation arises from a bidirectional flow, such as this, then we can prove, and we proved rigorously, so the following, let's say, so this is a schematic picture of the streamlines for the perturbed small amplitude waves. So there is an upper region here and the lower region here, and a region, enclosed by a critical streamline in which there is a stagnation point. So these are the periods, and here there are closed level sets. So this is the cat's eye pattern. So so these streamlines here are perturbations of this horizontal line here. So when the particle moves to the left, here the streamlines are perturbations of this horizontal line here, and particles move to the right, while these regions which for which the width of this ellipse, let's say, is very thin, so they do arise as a perturbation of the line of stagnation points that we had in the trivial flow. So this already occurs in the paper of Valens. So even for small amplitude waves, it has been proved that there exist waves with critical layers, and this is okay. All that I'm going to say about the streamline pattern for the constructed solution. So we have no results about how this looks like for large amplitude waves, but we expect something either of like here, or maybe possibly more complicated. Okay, so So our approach to derive this reformulation of the problem is to use a conformal mapping between a strip and the fluid domain. So this is the same approach that occurred in Adrian Nachbin's presentation. So so we introduce another plane in which we denote the variables by little x and little y, and simply regard the fluid domain as the unknown fluid domain as the conformal mapping of a strip through a holomorphic function u plus iv. Now, with the real axis being mapped into the free surface, and this other horizontal line being mapped onto the bottom of the fluid domain. And now, because the problem has the fluid domain has a periodicity structure, some periodicity structure will occur also in this for these functions defined on the strip. And namely, assuming for simplicity that the wave is symmetric, but with no other assumption on the geometry, there will be a rectangular box like this, which is mapped into one period of the fluid domain, and then with the next box here being mapped into the subsequent period, the preceding box being mapped into this period, and so on. So now, obviously, this strip is not unique, but the aspect ratio of the of it, so that the ratio of its sizes is always a constant, because we can dilate this strip, but we cannot just shrink it in one direction only. So things wouldn't work. And if we choose, so it is a natural choice that has been used by Andre, the period in the strip, the horizontal period, to be the same as in the original domain. So minus pi over k, then the vertical dimension would be a number which we cannot specify in advance, but it is determined by the geometry of the fluid domain, and which will be called the conformal mean depth of the fluid domain, and it will be a number h. So this line will be minus h. So there is an additional parameter arising in the problem. On the other hand, we prefer to work with functions of period 2 pi, and for that we make a dilation of this box. So instead of minus pi over k, we prefer to work on the interval minus pi pi, and then the vertical coordinate of the bottom will be minus kh. So so you should imagine that so our analysis will be carried out in such a strip of width minus kh with 2 pi periodicity. Okay, so the fluid domain itself is unknown, and so therefore this conformal mapping is unknown, and has it is the main objective of our of what we have to do. But looking at the boundary conditions that, for example, the imaginary part V has to satisfy, so because V maps this strip to the fluid region and this line into the bottom, so we have here V equals 0, and obviously V is harmonic. And then the restriction of V to the real axis, we call it little v. So little v, which is what I want to get, is a function of one variable, being the restriction of capital V to the real axis. Now, I am now claiming that if we know a little v, then we know the entire conformal mapping. Indeed, this is so because we determine capital V by solving the Laplace equation with boundary conditions little v and 0. So we determine capital V in this way. Then we determine capital U as some harmonic conjugate of minus v, and so if we know this little v, we know the entire conformal mapping and we know the fluid region. So now such conformal mapping exists for absolutely any periodic region in the plane. The question is, given that in the fluid region we have this equation and the relevant boundary conditions to be satisfied, what are the conditions that that have to be satisfied by little v? So this is our approach from the fact that there exists a function psi in this domain satisfying the relevant equations and boundary conditions. We would like to derive an equation for little v. And okay, also because of this consideration with conformal mean depth, we get that the average of this v is h. I'm not going to insist on how we prove this, so let me skip this. Okay, so it will be now important to discuss a little bit of complex analysis in a strip and to introduce our Hilbert transform. So instead of this u plus iv, I'm going to work with a holomorphic function z plus iw, and instead of this kh, I'm going to work with d. So let's say that we in a strip of between the lines y equals d and y equals 0, we have a holomorphic function z plus iw, where the restriction of capital W to the real axis is little w. So given periodic function w, so which will play a similar role to this v here, capital W is obtained by solving the Laplace equation, and then z is constructed from w using the Cauchy-Riemann equation, so that z plus iw is holomorphic. So in the same way, u is constructed from v, and so if w has average 0, then the restriction of z to the real axis will be a function of one variable again, so which by definition will be the Hilbert transform of w associated to this strip of with d. So it is well, usual way of defining the Hilbert transform. So you are more familiar probably with the disk or the half plane. So the boundary values of the real and imaginary parts of a holomorphic function on the in such a setting are related by the Hilbert transform. So on the other hand, if the function is not 2 pi periodic, then z will not be periodic, but will contain a multiple of x, and because of the Cauchy-Riemann equation, so the x derivative of z is equal to the y derivative of w, and is equal to, if we look here, so this constant plus the Hilbert transform of the derivative. While the mapping w goes into wy, so is the usual Dirichlet-to-Neumann operator. So so the Hilbert transform of the derivative corresponds essentially to the Dirichlet-Neumann operator, while the Hilbert transform itself achieves the correspondence between the boundary values of the imaginary and real part of a holomorphic function. So this is why our objects are relevant for our investigation, because we have we have analytic function in such a strip. Okay, so it is not difficult to find the explicit formula for this finite depth Hilbert transform. So it is a linear operator, and so if we look at the its action on the trigonometric system, then all of these problems, finding w from little w, finding z, finding the Hilbert transform can be solved explicitly, and we get this kind of formula. So this is a Fourier multiplier. On the other hand, as we might expect, so this operator also has a representation as a principal value integral, so obtained by taking the convolution of w with a certain function. Now, although this should be known, so we have not found it anywhere, and so here we have an explicit representation of this function that occurs in the convolution, in the definition of Hilbert transform. So it is the sum of a series, and the important thing is that so it is smooth except for singularities at the multiples of 2 pi. The singularities are of the right type, like 1 over s, and if we let d goes to infinity, we can find this limit, and it is a cotangent of s over 2. So in the infinite depth limit, we get the usual Hilbert transform, which is convolution with cotangent over 2, and that occurs in Babenko's formulation, and that has been used in Buffoni, Denser-Toll, and work. So if you know any reference where this appears, I would be very interested to hear about this. So this we just derived ourselves, and yeah. So even the irrotational waves of with infinite depth, this equation has not been studied before, although the theory is not very different from that with infinite depth. Okay, so how do we arrive at the equation that I announced? So because the equation delta psi equals gamma, we can relate psi very easily to a harmonic function. So if we subtract gamma over 2y squared and just add a constant, so we get a harmonic function in omega. Now, harmonic functions are invariant under conformal mapping, and for this function, maybe I could write some equations here and boundary conditions, and we can move everything to the strip. And this new function zeta, so will be harmonic, will be 0 on the bottom, will satisfy some Dirichlet boundary conditions, and this is what comes out from the Bernoulli condition. Okay, and all of this can be written in terms of our little w, namely this vx square is v prime square, this vy is ux, and ux was the Hilbert transform of v, so this will be 1 over k plus ckh v prime, while here, so zeta y is the Dirichlet-Neumann operator applied to this function here. So we start with Dirichlet data m minus gamma 2 over square, solve the Laplace equation, and then take the normal derivative. So this will be the Dirichlet-Neumann operator applied to this, and we get, I believe, this formula here. So this is our the first equation that we derive in an equivalent way, transforming the original problem. So this is the same equation that Andrea had in his talk, with our little v being denoted by a capital Y by him. But this is not the Babenko equation, so as we can see, this is a quartic equation, so we have quadratic terms here and squared. So we look at which powers of v and its derivative arise, and it is power 4. And Babenko equation that I presented at the beginning is an equation where which is cubic. So it is different from this one. So I wrote again the equation on the previous slide, and then I am claiming, and we have proved, that this quartic equation is equivalent to the cubic equation that I presented earlier at the beginning. So I am reproducing it here. And the second condition is just that the average of this first equation is 0. Yeah, so the water wave problem in the first instance is equivalent to this, but then we prove that it is equivalent to this, and this is non-trivial and involves ideas from so-called Riemann-Hilbert theory. And as I mentioned earlier, so the connection between V and the free surface is that if we know V, we can reconstruct the free surface in this way, with imaginary part V and the real part essentially the Hilbert transform of V plus some multiple of X. But this equation is actually more general than the water wave problem. So if we can find solutions of this, we do not necessarily get physical water wave, but one needs to have in addition a non-self-intersection condition for the above parameterized curve. So we need to find solutions of those equations for which this curve is injective and contained in the upper half plane. So if we just solve that equation, we would have solution with self-intersections. Okay, but momentarily I will ignore this requirement and just concentrate on solving this equation. So here I should say, and we are able to do a global bifurcation for this equation, while we wouldn't be able to do global bifurcation for this equation. So because of, as I'm going to show shortly, because of the need to prove some, to satisfy some compactness assumptions that can be proved here, but cannot be, at least we have not been able to prove them for this equation. Okay, so this is what you get in a more elementary way. This is what you get after a bit more work, which is not, so this is not just algebraic rearrangement of this. So it's based on a new idea, but this already, so if gamma equals 0 and depth is infinite, this is a Babenko equation. So this was essentially known for gamma equals 0. Okay, so our main tool for global bifurcation is the abstract theory of Dancer, Buffoni, and Toland, so which is bifurcation theory for a real analytic operator. So key assumption is real analyticity. Usual setting of bifurcation problems is that we want to solve f of lambda of u equals 0, where it is known that f of lambda and 0 equals 0. So where lambda is a real number and u belongs to a certain Banach space X, and this is 0 in a certain Banach space Y. So we already have a trivial solution. So these are the assumptions of the Buffoni-Toland-Dancer theorem. So at some point here, so first the assumptions of the Crandall-Rabinovitz theorem are satisfied, so which ensure the existence of a curve of additional curve of solutions in a neighborhood of this bifurcation point. So these are the usual So the linearization has a one-dimensional kernel, a range of codimension 1, and the transversality condition. So this is the assumption of the Crandall-Rabinovich theorem. And in addition, the operator needs to satisfy some compactness properties, which this one here, roughly speaking, says that the solution set intersected with a family of bounded closed set, with each member of a family of bounded closed set is compact. So, or in brief, bounded solution sets are compact, we can say. And also the linearization at every solution has to be a Fredholm of operator of index 0. So these are the assumptions, and key assumption is real analyticity. Then under this condition, the Buffoni-Dancer-Tolan theorem is saying that so there exists a global curve of solution, so which extends the Crandall-Rabinovich curve. Okay, so we have some asymptotic behavior here close to the bifurcation point. The important thing is the global behavior. So this curve is either a closed loop, so it returns to the original value, or otherwise it has to leave all of the closed sets that we described earlier and whose union was U. So this more informally can be said that the solution curve either goes to infinity in function space, or it approaches the boundary of the domain, or something like that. So the assumptions being real analyticity and compactness. And this is what we are able to show for our equation involving little w. So we had one parameter family of trivial solutions, which essentially can be identified with a straight line. So although they are not a straight line, but this is not important. And so along this line, we can identify a sequence of points indexed by the integers, all of which are local bifurcation points, and in fact global bifurcation points. So so the Buffoni-Dancer-Toland theorem applies in our situation. So we get, as I said, this a sequence of global curves, which either they are closed loops. So for each of them, we can say, so I'm just applying the abstract theory in our water wave situation. So either, so for each curve, either it is a closed loop, or it goes to infinity, or to the boundary of the domain in which the problem is formulated in the function space. So this is a so we work in Hölder spaces, C2 alpha, and symmetric functions. So this expression going to 0 means that this norm is going to infinity. So this corresponds to curve going to infinity. And the set in which the problem is formulated is the set where q minus 2gv is greater than 0. And the meaning of this q minus 2gv is that, so in the physical problem, it corresponds to q minus 2gy, which is gradient psi squared. And so this has to be always greater or equal than 0, and we assume it greater than 0. So the 0 case would be would be special. So this is the set in which the problem is formulated. And as I said, application of the Buffoni-Dancer-Tolan theorem leads us to either to a loop or a curve of solution going to infinity, or approaching the boundary, so which means q minus 2gv going to 0 waves approaching a stagnation point at the crest. So the fluid velocity at the crest, gradient of psi, goes to 0 along this family of waves, let's say. And and so we are able to apply that theorem. To be able to apply it, it was necessary to check the compactness assumptions. And now, so I'll briefly explain why the compactness assumptions are satisfied. So this Hilbert transform preserves Hölder regularity of functions. So it maps Hölder spaces into themselves. And so we look at the terms with the highest numbers of derivatives in the equation. And the highest numbers are these with v prime. Yeah, so only first derivatives we see. But apart from one of them, which occurs here, so all of the others occur in this kind of combinations, which we call commutators. Yes. So in particular, all the terms that are present due to the vorticity occur in the form of commutators. So and such expressions have the nice property that the difference of so similar object, yes, so here v square is inside and here is outside of the Hilbert transform. So they are smoother than, so the difference is smoother than each individual term. So if our function has n derivatives, then each of these loses one derivative, but the difference, so it can be proved, it is known, so only loses a little bit in the Hölder exponent. So these terms are smoother than they might have been expected at first sight. And so this means that between the left-hand side and the right-hand side of the equation, there is a lack of balance in terms of the regularity. So one term is smoother than the other. And so as we stay away from stagnation, so we assume this to be away from 0, so we divide by it and add some v's so that we get an invertible operator, let's say, and we can invert, and then we get an equation of the form v equals nonlinear compact operator, because the expression in the right hand side has one more derivative than v, because of the so here we don't lose any derivative, but inverting this operator we gain a derivative. And so our problem can be written as one of a fixed point of a nonlinear compact operator, and so this is sufficient to ensure the compactness assumptions required by the Buffoni-Dancer-Toland. And with this observation, we can prove that any solution is actually C infinity by a bootstrap argument. So the regularity improves. It's standard argument. Okay, so then this was about the existence of this family of the solution curves. And now we looked in more detail at the solutions corresponding to n equal 1 and minus 1 in the. So as I said, they are indexed by the integers, and so along this curves, v had close to the bifurcation point was like h plus s cos x or something like this. So this is for n equal 1 and minus 1. So these are essentially monotone functions, while all the others have here cosine of nx, and which have more oscillations on a period. So it is easier to study just the monotone functions corresponding to the first two curves of solutions. And so we were interested to rule out the possibility of loops, that these curves return to the original value. So such arguments are known, so have been used in other settings in water wave theory, and So this possibility is usually ruled out by showing that the solutions preserve a certain monotonicity that they had close to the bifurcation point. So on this part of the curve we had v prime less than 0, while on this part below we had v prime greater than 0. So if we could prove that v prime less than 0 is preserved all along the curve, so then in particular it means that it cannot return to the bifurcation point through the other side. So yes, so we try to prove such preservation of monotonicity by means of maximum principles, and also recall that our solution, so these solutions were physical only if this this curve was injective and contained in the upper half plane. So we examined those properties as well. So and we said, well, let us see. So monotonicity holds close to the bifurcation point, and also the curve is in the upper half plane, and this condition here in the presence of monotonicity is actually equivalent to injectivity. Namely, the curve is, so I am always assuming symmetry. I forgot to mention this. So we have symmetry, and the curve is also periodic. So, and because of periodicity and symmetry, it is enough to study what happens in half a period of the wave, because then the curve can be obtained by symmetry and periodicity. So if v prime is less than 0, so this means that the curve always decreasing. And in half a period, it is a curve like this which always decreases. It is injective in half a period. So now, if we reflect it and also extend it by periodicity, when could this fail to be injective? Well, so it is obvious if and only if the curve touches either this axis here, x equals 0, or the touches again the trough line. So because if it is like this, then on the other side it touches as well, so it has a self-intersection. While if it reaches this line, then by symmetry it reaches it again, so again it has self-intersection. But yeah, so this is x equals 0 and this is x equals pi over k. But if the and this expression here gives the horizontal coordinate of the curve. But if we stay between these two lines without touching them and with this monotonicity, then we have a global injectivity, because there is no way for the curve to self-intersect. So, so these properties are true for the solutions of small amplitude, and we studied to what extent they remain true along the solution curve. And obviously there are two possible situations. So they are always true, or they are not always true, in which case there is a first point at which one of them fails. Yeah, so all the time, or there is a first point at which they fail. But at this point of failure, so the strict inequalities transform into non-strict. So all of this greater becomes greater or equal, and so on. And we were able to prove that at this first point of failure, of where the inequalities, some of them become non-strict, so actually precisely one of the four, it is the one that becomes non-strict. The others continue to remain strict, and namely, so this is the situation. So it is we have equality here, while here is strictly less, strictly less, strictly greater. So what does this mean? And the equality here means that the solution curve reaches the vertical line x equal pi, and therefore it reaches it on the other side, so it has a self-intersection above the trough line. So the two alternatives that we have is either the solutions are physical for all values of the parameter, or there is a value of the parameter s along the curve, at which the solution is almost physical, except it has a touching point exactly above the trough line. And this is in a perfect agreement with the numerical simulations that have been carried out by people. So in computations, so such waves touching above the trough have been calculated. And so so what can happen to the, as we go with the parameter towards infinity along this curve? So our conjecture is that this q minus 2gv, which was always greater than 0, so actually approaches 0 at the highest point of the wave, and at such points it is known that the wave is not smooth, but it would need to have corners of 120 degrees. So as the parameter goes to infinity along the solution curve, there are in principle, three possible limiting configurations. A monotone, yeah, I'll finish in 2. Monotone wave with the corner, overhanging wave touching itself above the trough, and overhanging wave which is injective but also with a corner. So which of these situations happens seems to depend both on the size of the vorticity in relation to the other parameters in the problem, and also on the sign in relation to other things in the problem. So here we are planning to continue to work on this, but this is the current state of the rigorous results known. So Andre and the collaborators have done some relevant numerical calculations exactly for this problem, but as far as I understood from his talk, so his results do not answer clearly which of these situations occur, because they have not really computed overhanging waves with a large amplitude. So yes, so this is all. Thank you.
Answer a couple questions.
Because I don't have time, we don't have time, just a short comment. According to my computation, the loop exists when k is greater than 1. And k is 1, loop is unlikely. That is my experience.
You mean the period?
Yeah.
But there has to be some relation with gamma as well. So
of course, yes.
So something with, okay.
There are many loops appears. Yeah.
Yeah, I'd be very interested to discuss about this further, yes.
So do you get overhanging curves this way?
No, we are not sure that. So the formulation is able to capture overhanging, which previous formulations did not. But we do not know whether the solutions we construct are indeed overhanging or not. Yeah, no.
Is it like the solutions that you get bifurcating from the?
Yeah, from this.
The others, or that's expected to be all of them. The ones that bifurcate from the.
So they bifurcate from this kind of flows that yes, and as the amplitude increases, so at the beginning they are small perturbations, but then the amplitude increases and we don't really know Okay, how the shape evolves, but so the theory is giving us the existence of this global curve of solutions, but in principle there could exist secondary bifurcations even of, so there is no known results about this. So this is not ruled out, let's say, but that, yeah.
But we have example of overhanging numerical solution.
Yeah. I think I mentioned your. Yes, and even in the. Yeah, so this is your book, and Teles da Silva and Peregrine, and yes, so we have seen, I mean, I am fairly certain they exist, but our analysis so far does not give a proof yet. But yeah.
How do you exclude that along this curve the wave profile does not touch the bed?
So we look at this at the first point where this might happen. So as I said, so there is one point at which this might become zero at some point, but at that point I think we use Hopf lemma or something. So it's a very simple argument. So it would have to touch at one point while remaining above at all the others. So that point will be some sort of maximum and minimum, and by Hopf you rule it out. So all of these other possibilities are ruled out in this kind of manner. Maximum principles and Hopf and the Serine corner point, and yeah.
But if the curvature blows up or something,
we can talk about this, but this is in our paper, so it is proved.
Can you deal with bottom topography using the Babenko method? It doesn't seem that the top surface is any different. Why does the bottom one have to be flat?
Okay, if it is not flat, then you don't have the trivial solutions that we started from. So, but
you could presume that you start with some solution.
yes. So in principle, version of well.
We change the topography as a parameter in the top.
Yes, you are right. So the problem makes sense, but it is well. But then it was crucial that our function is zero on this line. So otherwise, we would have some other Dirichlet boundary conditions, and which would not actually be known for sure. So it would complicate matters a great deal.
you know the bottom boundary condition. Even if it's not flat, you know the bottom boundary.
No, but this is about the conformal mapping. Yeah. So we ignore the equation. So we know that V will map this line into some curve, but U and V together, yes.
The reason that I ask is that Krzyzewski deals with bottom topography in his 1960 paper, and that's conformal mapping as well, where the bottom is a prescribed fixed domain.
But also periodic, probably, otherwise.
Periodic.
Okay.
Well, he does the sultry wave case as well, sultry waves over a pump, but for the periodic case, he has a prescribed bottom periodic topography and looks for free boundaries above it, and he uses a conformal mapping.
I think that there would have to be, as an unknown, also a parametrization of the bottom. So maybe like in your hydroelastic, yes. So it would be much more complicated, I would say.
Any more?
What can you say about limited?
Say it again.
Limited wave.
Limited.
What corner on the curve?
120. Yes. This is known. I mean that if it has a stagnation point and it has, if it has some monotonicity, which we know in this situation to have, yes. So this occurs in some papers, some recent papers of mine. So the vorticity does not make any. any difference.
There is Gerstner wave with angle 0.
Yeah, well, there the vorticity becomes infinite, and that's the reason. So so this corner of 120 is true for bounded vorticity. If it becomes infinite, and then the vorticity dominates compared to the.
Any more? Stimulated a lot of discussion. Well done. Thank you very much for an interesting talk.